Hello Chem 1A, this is Chapter 4, Lecture Video 6, and we're going to be talking about neutralization reactions. So first we need to talk about strong acids and strong bases. Strong acids and strong bases, like I've mentioned in the beginning of Chapter 4, are strong electrolytes, meaning they dissociate 100% into ions. So how do we tell what are our strong acids? Well, it's pretty easy. There are only 6 strong acids out there, and they're these 6, right? So hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. These are our 6 strong acids, and you should know their names and their formulas, and you should have memorized because there are huge numbers of weak acids out there, and so it's a lot easier to memorize these 6 because that's kind of how we determine whether an acid is weak or not. We memorize the 6 strong ones, and anything that's an acid that's not one of these 6 is by default a weak acid. So we also need to memorize, I really kind of should just scratch this out. Memorize is a strong word. These are the 4 strong bases that I will use. There are more of them. And basically, the deal here with strong bases is they contain hydroxide and they're soluble ionic compounds. Technically, any soluble ionic compound that contains OH- is a strong base. These are the 4 that I would be using in any test questions in our class. These would be the same 4 that I would be using if I was teaching Chem 1B for you as well. So you should probably know that these 4 are definitely strong bases. Memorize, you should just be able to recognize them. So let's talk about weak acids. Anything that is not a strong acid is a weak acid. So pretty much by definition, we memorize those 6 strong ones. Anything that's not one of them is weak. Now what does it mean? Strong acids, like we talked about, dissociate or ionize 100%. Weak acids generally are pretty much the opposite. Instead of ionizing 100%, in other words, if I had 100 weak acids, maybe 5 of them ionize. So usually we're looking at like a 5% or less ionization of the substance, right? So only about 5 out of 100 weak acids will actually break into ions. This is really the difference between a weak acid and a strong one. In a weak acid solution, basically, like I said, very little of the acid's actually going to break apart into ions. Because of this, they are not strong electrolytes, and when we're doing net ionic equations or total ionic equations, we do not break weak acids into the ions that make them up. This is an important distinction between neutralization reactions and precipitation reactions when writing net ionic equations. Okay, so neutralization reactions are the reaction between an acid and a base. Now, there are really 2 major types of neutralization reactions that we're going to do net ionics for. And that's a strong acid reacting with a strong base and a strong base reacting with a weak acid situation. Now, as a general rule, all acid-base reactions tend to form the same types of products. We pretty much always form an ionic compound or a salt and water, H2O. And we can see that in this generic type of situation, right? An acid is just really a hydrogen attached to some kind of anion, and our bases are most of the time just going to be a metal attached to a hydroxide. Now, if we look at this, this is a double replacement reaction. The metal is going to attach to the anion of the acid. The acid is going to attach to the OH. This forms Ma, metal, cation, anion that was attached to the acid, and HOH, which is just a fancy way of writing H2O, water. So again, double replacement reaction. Let's use actual substances now. We have a strong acid here. We have a strong base there. When we write out this molecular equation, we have HBr reacting with KOH. They're both aqueous. We're going to form KBr, right? Because the K is going to attach to the Br. The OH is going to attach to the H. This gives us H2O. One of my biggest pet peeves is when students write aqueous next to water. This is not okay. And so you need to put liquid next to water because aqueous means dissolved in water. And you can't dissolve water in water. That's just pure water then, right? So don't write AQ next to H2O. It doesn't make any sense. Okay, so now let's break this up into our total ionic equation. Again, when we're separating compounds into ions from a molecular to a total ionic equation, remember that we're always only separating the strong electrolytes. So we need to determine which things are strong electrolytes in this reaction. Now HBr is a strong acid, so it's definitely a strong electrolyte. KOH, strong base, definitely a strong electrolyte. KBr, soluble ionic compound, definitely strong electrolyte. H2O, molecular compound, non-electrolyte. Right? So this guy doesn't get split up, but everything else does. So we break up HBr into H plus and Br minus. We break KOH into K plus and OH minus. We break KBr into K plus and Br minus, and then we just add water on at the end, and we don't separate it at all. Now we're looking for spectator ions, right? Here I have K plus, I have K plus, I have Br minus, I have Br minus. These two are my spectator ions, so we're going to get rid of them to get our net ionic equation, which is going to end up being H plus OH minus goes to H2O. All strong acid and bases, when reacting with each other, always simplify to the same net ionic. But if one of them is weak, we get a much different net ionic equation, and this is an important distinction between when we have strong reacting with strong versus strong base reacting with weak acid. So let's do an example of that. So when we have a weak acid or a weak base present reacting with something strong, the net ionic, again, the thing that's weak does not get split up into ions when we do the total ionic equation. Now, we're not going to work with weak bases in this class. That's going to be a Chem 1B thing. But you will be responsible for writing a net ionic of a weak acid reacting with a strong base. Let's say acetic acid, HC2H3O2, reacting with KOH, potassium hydroxide. This is a strong base. This is a weak acid. Now, when we write out our molecular equation, right, we have this weak acid reacting with KOH. It's going to form, the K is going to attach to acetate, the OH is going to attach to H. We're going to get water and potassium acetate. Potassium acetate is a soluble ionic compound. And so now we need to figure out what things split up into ions, right? Remember, it's strong electrolytes only. Now you can't just rely on aqueous here because this is a weak acid, and weak acids do not break apart into ions. Even though it says aqueous doesn't mean it's a strong electrolyte. So this guy does not get broken up into ions. The rest do. KOH, soluble ionic compound, broken up into ions. Potassium acetate, soluble ionic compound, breaks apart into ions. Water, just like last time, is a non-electrolyte, so it does not. So when we write the total ionic equation, we just leave acetic acid the same as it was in the molecular. KOH breaks apart into K plus and OH minus. Potassium acetate breaks up into K plus and acetate, and then we have water there at the end. Now we're looking for our spectator ions. I see that I have a K plus on both sides, but that's it. So when I cancel them out, my end-all net ionic equation is going to be acetic acid reacts with OH minus to give me acetate and water. Okay, so if you have any questions, please let me know. I'm always happy to help you. We can set up Zoom meetings by appointment, come to office hours, what have you.